What is up, guys? Today, welcome back to another CCT video. Gotta get my intros down. Today's a pretty good day. The Bills just went out with a win. Kyle Williams is retiring, and he got quite the standing ovation today. He is a defensive lineman. Even they threw him in as a running back, believe it or not, and he ran 10 yards for a first down. So, yeah, that's Kyle Williams. Also, if you'll remember from last, it was last year, from 1 year ago, from today exactly, I think. Kyle Williams pushed us through for a touchdown, and which ultimately pushed us to the playoffs. It was very clutch, and we owe you a lot, Kyle. So have a nice retirement, and yeah, enjoy the rest of your life. Okay, so for today we are going to do binary tree level order traversal number 2. Okay, so let's explain what's going on here. This is a binary tree problem we got here. We got this tree, and what we want to do is print out, or not print, we want to make a vector of vector ints representing each row. In reverse order, shall I say. I really don't get the point of reverse ordering them. I have a way to do it that's frontwards ordering them, and then I'm just going to reverse the vector. That seemed to work well. Okay, let's get to our drawing board. So, the color of the day is going to be magenta. A nice magenta. I like that. Yeah, that's good. So, let's see. We have a tree. I'm just going to draw it like this. I don't really want to draw numbers, so. And that, and then like that, and then that, and that, or something. Okay, so we want to print out these, each row as its own vector of ints. Okay, so in order to do this, something to think of that at least popped into my head first was a breadth first search. Breadth first search is when you you look at the nodes in this order. You go like here, then you go through the first row, then you go to the second row, then you go to this third row, the fourth row, and that's the order that you do that. Versus a depth first search, which is going just all the way down first, and then it goes all the way down, and then here, and then there. Oh, wait, no. It goes all the way down first, then here, then back up here, then all the way down here, then it's kind of like that. Let's just get rid of those excess lines. Okay, but breadth first search is row by row, which is kind of what we wanted. However, there is something tricky here. You're like, so when you go, so in breadth first search, you use a queue. So queue is a data structure that you push stuff on the front. Sorry, you push stuff in the back and you pop towards the front. So you push here and pop here. So this is a queue. I mean, this is a line. You start at the back and you leave at the front. This is versus stack, where like a stack is kind of like a stack of plates. The first plate you put down is the first plate you take off. They kind of make sense. It's pretty smart. I think their names for it. So you use a queue, and what you do is you put the root node on the queue first. So q dot, I think it's push or something, root. And then what you do, you usually have like a while loop. while the queue is not empty, what you do is you get the top of the queue, so top of queue, then you pop the queue because you're using it, and then you add to the queue, or like first you could do something like here you could like do something. I don't know. If you're looking for something, if you're looking for a certain element, you can check if the value equals it there. But then the next thing that you're supposed to do is you're supposed to add all nodes connected to top. So it's going to add these nodes here for the first time, okay, in that kind of order. So then you have like, well, let's label these. So like 1, 2, 3, 4, 5, 6, 7. So first you had like 1 in the line, and then you popped 1, and then here you added all the nodes that were connected to 1. So you first put 2 in, and then you put 3 in. See, it's a line. This is the front of the line. This here is the back, right? That's how a queue works. You start at the front and go to the back. Then, okay, so here's the thing. One of the hard things with this problem is you have to know how many values you're expecting to put in this vector of ints before we send it to the solution. So this like do something is like making the vector, and then probably we should like then add the vector of ints to the solution. So the hard thing though is you don't know how many ints you're looking for. So you don't know how many nodes you're looking for. So like, let's say we got here. We already pushed back 1 as a vector to our solution. And now we're looking at 2. So we pop 2 off or something. Then we go here and we do something. And then we add all the connecting nodes. So then there's going to be 4 gets pushed back, then 5 gets pushed back. And then we come back here and we do the same thing. We pop off 3, and then we add 6 and 7. It's connecting nodes. But how, the problem is, how did we know to stop after 2? Like why is this first row, how do we know when to stop adding stuff to this first row's vector int? Like why couldn't we add here? So the one thing that you could do is, this is what I originally tried. I had a check here that was like, let's say current row. And then I had next row. And what this was doing, like when something was added to, it checked if these were possible. So first of all, it only added this the vector int once the vector was filled up to current row amount. And then I was modifying next row to be to just see how many of these were possible. And then when I was going to push back this vector int, I turned the current row into next row and set next row equal to 0. Let me show you what I did in code, because that was a pretty bad explanation. So I have this thing called nodes in current row and nodes in next row. And I basically, I had this row, and this row is what I'm pushing back to my solution every time. So the nodes in current row equals the row So only when the nodes in current row equals the row size did I get to push it back. That's how I was able to figure that part out. And current row got its size by being set to nodes in next row here. And nodes in next row was like if top left was so it was kind of like, did I start off on, yeah, so it was like, let's see, current row, yeah, I started off here, but like this is my current row, and I was waiting till I had two things in there. I mean, honestly, it was confusing because technically, here in the first iteration, I'm still at the root, and then I'm putting in the left and the left and the right ones, and so I'm technically here and filling in this row. And I take in these. I know that I'm only looking for two because that was my base case here. And then, sorry, this is a really terrible explanation, but yeah, bear with me. I'll get to my better, smarter implementation soon. So then you guys could skip ahead to that. Just trying to get my thoughts straight here. So we got top right left. So like as I'm filling in this row, I'm checking to see if this is like still the next row here. And I'm building up the next row. And so then once I get to this row, so now this row is current row, I am waiting to pop back these four. So like 2, 3 was already pushed into the vector solution. And so, but they're still currently in the queue. So I go through here and I'm waiting till I push back 4. So go here, I got my 4. And while I was doing that, I was also updating, does it have here? Does it have here? Then I got to the right, does it have here? Does it have here? No, it doesn't. So don't increment that. Okay, it was kind of a mess. So I have, now let me get to my better solution. Oh, wait. Okay. So this solution, in order to figure out, so if I have this again, then that, and that, and then that, something like that. I'm going to first push this one, and then in order to see, so I'm still going to use the queue stuff, and I'm going to push these two. Wait, no, am I going to do that at the start? Do I push those two back? So I pop. No, okay. So I'm here, and I get the size of the queue now, which is just so queue I'll put here equals just 1. So size of the queue is 1. So then I am going to do a for loop and pop through this and go through my 1 things that are in the queue and add all of these. Okay? So pop through, so my 1's gonna go in, and then I'm gonna be adding, so pop 1, then we get 2 and 3 are pushed in. And so the solution now has a 1 in it. And now I finished that. So now the queue is size 2. And now I am going to do a for loop through 2 of them and then pop the rest of them and add these. So then this gets popped, this gets popped, they both get put in here. And in that process they did 4, 5, 7. And now the queue size is 4, so we're going to go through this 4 times, popping all of them, and then putting all of these on the queue. So yeah, so that's the process we're going to do. I'm going to try to write this out now. So what we're going to do is first always start off with our solution, and we'll get to the base cases. Hopefully I can remember them. We're still going to have our vector of int called row, and we're still going to have our queue, which I just call queue of int. And then we're going to, no, wait, it's not a it's a tree node pointers. Then we're going to do push root, and then we're going to do while queue is not empty. Okay, int, here's where we go. Int size, we are going to capture the size of the queue right here. Okay, and then we are going to run our for loop that many times, popping everything out of this queue. That's what we're going to be doing. And also adding the new items like a regular breadthfirst search. So we have, actually, I think it might be better to just do it like that, so I don't have to clear it, you know. So here's what we can do. We can do auto temp gets q dot front, and then if temp can go to the left, let's do q dot push. So I am pushing stuff, but it doesn't affect this size. So if temp right is available, q dot push temp right. So I have not done anything to the row yet, so I should probably be doing row. Well, actually, I could do qpop here, and then row dot push back. I'm gonna push back. I already popped it, so I'm gonna have to go in the temp val. Okay, so then after that, I'm going to do sol dot push back row, and before I forget here, I do have to reverse this, sol dot begin, sol dot end. I don't know why they asked in that order. Return sol. Okay. So let's think about this again. So we pushed the 1 in. So we go in here, and the size of the queue is now 1. And now we're going to go through that one thing. And so we get the top of the queue just once because there's only one thing in it, and we add all the connecting nodes. Okay, so then that's probably it now, and then we just push back the row. And if there's nothing in the row right now, then we're done. However, if there is something still, like let's say it pushed back 2 things, so now our size is 2. So here's what we're going to do. We're going to take the 2, and we're going to push back all of its connecting nodes. And then we're going to do the same to 3. Notice we know exactly to go only 2 times. We know to go of the size of the queue right now before we started going to the next level. And we saved that with the size here. Okay, so one more thing. Let's try to think of, does this work if it's empty? No, it does not, because, well, does it? Yeah, I don't think you could push a null thing. So you could just say if not root return solution. Okay, I think this will work. Oh, I spelled vector wrong. Well, let's just run it. Okay, it worked there. That's a good sign. Always a good sign when you get that. Oh, great. Okay, so we got faster than 98.69% of people. That's great. I'm curious what their solution was. So, how do I see their solution? Oh, I can't see it. Okay, let's look at discussions if we see anything different. So just to understand what we're doing for breadth first search again, we have a queue, we fill it up with this row. Let's just say we're able to do that. And like we're here and we fill it up with this row. Or actually, better example. Let's say we are let me erase this. Let's say we are here and we're like going through this and we are now pushing this into the queue here. We're pushing these ones into the queue. So in order to, so like let's say our queue is currently 2, 2, 3 like this. And we want to turn this into a vector and push everything inside it. So we need to know to stop at 2. So to go through this twice exactly and just push whatever comes on board during this process, go for it. So we're going to go through this twice. We pop it, add everything there. Okay, so 4, 5. We're still only going through this twice, going through the queue twice. Then we get here. And 6, 7. Okay, we went through the queue twice. This is the queue, by the way. Okay, and so when we did that, after that, we turned this into a vector. And then we're done with that. So now the queue is not empty yet, so we are going to go through this. We're assuming this is the next row. Great. We're going to turn this into a vector and also add get prepared for the next row. So what we do is, let me just write this down here so we could see it a little better. Then what we're going to do is go through this 4 times and then like add it to the row, and then we're also going to add things to the queue still. So we're going to add, when we go to 4, we're going to be adding 9, 8. When we go to 5, we're going to be adding 10. When we go to 6, we're going to be adding 11. When we go to 7, we're going to be adding 12. Okay, so this is what's left in the queue, and now we push this back. Actually, we pushed it 4, 5, 6, 7 because we're accessing the queue this way. First, second, third, fourth. Okay, so now we have here. And we're going to go through this now 5 times. We're going through the queue 5 times. Whatever happens and whatever like gets added to the row, we don't really care at this point. So we get to the 8. Is there anything here? Nope, nope, nothing gets added. Okay, cross that off. 9, nothing gets added. 10, nothing gets added. 11, nothing gets. 12, nothing gets added. We put this in here. And then we check to see if the queue is empty. Yes, it is, and we're done. We're gonna reverse this though, and then we're done. Okay, so this is a breadth first search solution. It's probably gonna be similar to what I had. So while stack is, oh, you used a stack, even though you, how stupid is, why would you call your queue a stack? That is so ridiculous. I've never left a comment, but I think I'm gonna leave a comment. Why? Who does that? Okay, stacked up, push, root, current equals 1. While stack is not empty. It only has 3 views, wow. While current, okay. Kind of confused on what current is. So tree node temp gets the front of the queue. This is a queue. Result pushback temp value. Okay. His while current minus minus is the same as my for loop. And you see how it's updated here. Current gets count. And instead of looking at the size of the queue, he's just doing an incrementer. He could have saved a step by just looking at the size of his queue at this point. And also, it does not make sense to use while loops. Like, the whole point of for loop is if you know how many times it's going to run, or how many times you want it to go, you should use a for loop. Okay, so did he reverse it though? Because it seems like he has to. So then, what is he returning? So I don't know. I feel like he's reversing something. Okay, interesting. Recursive solution. Let's look at this. Recursives are interesting. See this, you are also reversing your answer helper, answer 0 root. Okay, so we got answer level node. So if size equals level, answer dot pushback Wait, that's weird. It's maybe for an edge case. Answer so answer at level Wait, you didn't even... He didn't do anything to level, like... I mean, he answers is... You can't just random access something if you didn't make the size of it. He never made the size of it. Maybe that's what this is doing. So he's like, because the size does equal 0, fine. So he pushed back this, and then, okay. Yeah, that is what he's doing. So if, that's so weird. So if, well, I guess you don't know how many levels it is, so I guess you have to do that. So then you do levels dot pushback node value, okay, helper. Yeah, this one's too much. This one's just too much. Recursive. Level order bottom. So you always also reverse it. Might be super expensive. It's really not. It's really not. So if level is greater than or equal to levels dot size levels dot pushback vector. It seems like he's doing a similar thing here. Order. Okay, so it's like kind of adding thing levels as you go. But this is just... Okay, so he's level order. So you're adding things, root left, level plus 1. And root right, level plus 1. Okay, and you're supposed to be adding those to the right things. So it's like... Okay, so... this is... So recursive is always like depth first search. So you add those. And depth first search really does not make a lot of sense. I'm not gonna lie, it does not make sense, depth first search. But, so there's always like a harder way to think about this. So you go down, and keep adding levels, and then go up one, and go to the right. So you go all the way down to the left. Okay. So here's what I'm seeing, what they're doing, because I just want to discuss this depth first search, because it's like, it's kind of an interesting idea. So depth first search is like, so it goes all the way down. I'll add a few more like that. It goes all the way down here. So it's gonna be not having a level here, not having a level here, not having a level here, not having a level here. So he just added from doing that one thing like 4 levels. Then, and when they don't have a level, he puts a level in there with the value. So he just added all of these to like row 1, row 2, row 3, row 4, and row 5. Then he's going to go up here, and so like think of this like we're in the 4th iteration. Then he goes here, and so we're in the 4th iteration here. And we just added a 5th level from the left side going here. Then we go to the right side, and we also add a something here to that level. And here it exists, so it actually exists because wait, level is greater than or equal 2. Wait, how many low? This is 1, 2, 3, 4, 5. It's 5, and then why would it be greater than or equal to? I feel like it should just be greater than. That is weird. So we're at the 5th level here, and the size should be 5, so they equal each other. Yet you want to go. I'm kind of curious about this now. So let's put in this depth first search here. Okay. I feel like that would mess it up terribly though. Like, what about? I mean, I guess this isn't gonna work, but just give me an example, you know. Runtime error. Okay. Okay, with their example of 3, 9, 20, no, 15, 7. I was like, but like, okay, I guess it doesn't work with anything though. So levels start off at, oh, levels is zero-based indexing. Right, got it. Level is zero-based indexing. The size of levels is going to be like 5, and level is going to be 4. Sorry. Yeah, 4 here, which is good. If level was 5 here, that would mean it's like out here, and that would be a problem. So, yeah. So that's why it's greater than or equal to. So then after goes here, puts it into that one, then goes back up. Now we're like at the 3rd iteration you could think of, and we just completed the left side, and now we're going to the right side, so then it comes up here, and then it does equal, because right now the level is, I should make this like 0, 1, 2, 3, 4. So now the level is 3, which is less than 5. So we go here, which is saying at 3, push back that. So it's pushing back that. This is interesting. I do kind of like this. Yeah, I kind of like it. It definitely makes more sense to use breadth first search, but that is cool. Okay, let's put this back so I feel better about myself. Alright, so thank you for watching another episode of CCT. Remember, this is a relaxing thing. Make sure you watch it, you know, while you're walking your dog, while you're going to sleep, wherever you want. Well, hope it helps, and I hope I got you a little more prepared for an interview. Alright, see ya.